We can start, yes. Okay, so uh, nice to see everyone. I hope you see my screen. So today a lecture will be devoted to dual coalescing stochastic flows on the real line. Last uh, lecture we constructed a pretty large class of coalescing stochastic flows. Now we will look at dual to flows and how one can use them. Okay, so we already had the definition. I reminded that dual flows are backward flows in the sense that these are family of mappings indexed by TS when S is less than T, meaning that the backward flow acts backwards in time. And if we change time from, let's say, from TS to minus S minus T, we get the usual flow. So a backward flow is just a usual flow, but indexed backwards in time. And a backward flow is called a dual to the flow psi if the following inequality holds for all moments of time st and for all points x and y. This inequality means that trajectories of the flow psi and of its dual flow psi tilde do not intersect. So they can touch each other, like on this picture, but the dual flow cannot, for example, start above x and be below psi of x at time t. So this is prohibited by the definition of dual flow. We will see that in some sense a dual flow is a generalization of the inverse mapping. For a stochastic flow of mappings of the real line, because of the flow property, mappings are increasing. They may not be one-to-one. However, for every increasing function, we can define the pseudo-inverse function. Actually, there are two natural choices. So V plus is the infimum of x. It must be psi here and here. V plus is the infimum of such point x that psi of x was strictly bigger than y. And v minus is the infimum of x such that psi st of x was greater or equal to y. These are so-called pseudo-inverses of psi. V plus is right continuous and V minus is left continuous. And one can check that a backward flow psi tilde is dual to the flow psi if and only if this mapping psi tilde is so it takes its values always in the between V minus and V plus. In particular, if we have the flow of homeomorphisms, then V plus and V minus are equal, and they are actually equal to inverse mappings. So when we have the flow of homeomorphisms, the dual flow is just the inverse flow. What about the coalescing stochastic flows? An interesting observation was made by Aratia. He noted that neither V plus nor V minus satisfies the flow property. So neither of them is a stochastic flow. Also, he noted that the distributions of V plus and V minus are equal, and actually they are equal to the distribution of the Aratia flow. So it is a natural question to ask, can we actually construct the dual flow, for example, for the Aratia flow, or for more general coalescing stochastic flows? Let's see, for example, why V plus is not a stochastic flow. Let's consider the following picture. So assume that this is a one trajectory from the Aratia flow. This is another. They have coalesced at some moment of time. And let this be moment R. This will be S. And this will be time t. Let this be the point y, and assume that it happened such that all trajectories that started below this point, they arrived strictly below y. Okay. Let this point be x, this will be x tilde, and this will be y tilde. Then V plus ts of y is equal to the infimum of all trajectories that started at time s and bigger than y at time t. And from the picture, we see that v plus ts of y is equal to tilde y. Now, if we apply v plus sr to tilde y, we need to compute the infimum of all trajectories that started at time r and bigger than tilde y at time s. So v plus is greater or equal to x tilde. On the other hand, v plus tr of y is less or equal to x. Okay, y is, let's take y here. Yes, then then indeed v plus ts of y is tilde y. V plus SR of tilde y is tilde x is greater or equal to tilde x, and V plus TR of y is less or equal than x. In particular, we see that V plus TR is not equal to the composition of V plus SR and V plus TS. So these two natural choices of pseudo-inverse functions may not be flows. Okay, now let's show under which condition the dual flow exists. And we will do this on the space of coalescing flows that we introduced yesterday. So this is the space of all families of continuous functions that start at all space-time points S and X. They satisfy the flow property. This is property number 1. Property number 3 is that the trajectories that started strictly before time S form a dense set at time S. Property 5 is right continuity at the so-called fresh points. Yes, so at all points of the that are not images of trajectories that started before time S. And I will add 2 more properties to this space. Property number 2 says that the image of the real line under the mapping psi is a locally finite set. It means that if we consider a mapping that acts from time S to time t, in the image we have a locally finite set, meaning that every segment contains only finite number of points of the image. And all points from the real line from time S, they have coalesced into this locally finite set at time t. Also, we assume that this set is unbounded from above and from below. This is exactly the property that that have, for example, Aratia flow or more general coalescing stochastic flows that we constructed yesterday. And the most restrictive property, and this is quite fine property, that mappings from the flow, they don't have two-sided discontinuities. So every mapping psi st at every point x, it is either continuous from the left or continuous from the right. Okay, so this will be our space of flows. So I stress once again that all properties except number 4, they are satisfied by stochastic flows with transition functions Pn that that satisfy assumptions from the previous lecture. Okay. to construct the dual flow, we will use these generalized inverse functions, v plus and v minus, and let us know that these functions are well-defined, finite, and continuous. So as a function of s, the both generalized inverse functions are continuous. So this is point ty. Here goes, let's say, v plus ts of y. To see that it is continuous is actually quite easy, because at every point s, by the denseness property of the flow psi, we can find one trajectory of the flow that goes strictly above this point, and another trajectory of the flow that goes strictly below this point. And since v plus cannot intersect the trajectories of the flow psi, v plus must be bounded from above and from below by these two trajectories, and this shows continuity. Okay, and now let's define the dual flow. To do this, we need a classification of points. So let's consider a point ty. It is called left regular for a flow psi if all mappings psi tu are left continuous at y. If this is not the case, a point is said to be left irregular. Under our assumptions that we have a coalescing flow, that images of mappings are locally finite, it follows that if a point is left irregular, then it is regular in the sense that all mappings from t to some time u will be right continuous at this point. So this follows from locally finite images, and it follows from the fact that mappings from the flow psi, they are either continuous from the left at every point, or they continuous from the right at every point. In fact, one can easily check that a point is left regular if and only if all mappings psi tu, they have a segment like below y that sticks to the trajectory that starts from point y. And for left irregular points, the analogous segment is on the right side of y. And now let's define the dual flow. So for all s, t, and y, we look at the point ty, and if it is left regular for the flow, we define dual as v plus. If it is left irregular for the flow psi, we define the dual as v minus. Then by construction, psi tilde is either v plus or v minus. Yes, so trajectories of psi tilde are continuous functions that that do not intersect trajectories of the flow psi. And also note that for all s less than t, the mappings psi tilde are defined in such a way that either all of them are v plus or all of them are v minus. Yes, for fixed ty. So the only thing that must be verified is that psi tilde is actually a flow of mappings. Okay, and let's try to do this. So we fix 3 moments of time, R, S, and T. Here we have a point Y. Then here we have the mapping psi tilde that starts from the point Y. Its value at time S we denote by Y tilde. Its value at time R we denote by X. And the flow property means that if we act by psi tilde SR on Y tilde, we must get X. Yes, so the flow property means that if we act by mapping psi SR to this point, we must arrive to X. Assume this is not the case. Assume actually that X is less than tilde X, meaning that psi tilde takes Y tilde to X tilde, which is bigger than X. Then we can take a point here, point Z. Now let's look at some properties of Z. So the point Z is bigger than X, okay, and X is a psi tilde of Y, psi tilde TR of Y. We have defined psi tilde in such a way that it is either V plus or V minus. In any case, psi tilde TRY is greater or equal to V minus TRY. Recall that V minus is the left continuous generalized inverse. In particular, this inequality implies that psi RT of Z is greater or equal to Y. Okay, so we have this inequality. Then Z is less than tilde X, and tilde X is by definition is psi tilde SR of tilde Y, and it is less or equal than V plus. So psi RS of Z must be less or equal than tilde Y. Okay, then assume that here we have a strict inequality. Then psi RS of Z is strictly smaller than tilde Y. On the other hand, tilde Y is psi tilde TSY. So this is less or equal than V plus TS of Y. And this is bigger than psi RS of Z. Okay. So from these two from this inequality, it follows that psi st of psi rs of z is less or equal to y, but this is psi rt of z. And we deduce that psi rt of z is equal to y. Now, let's consider the point tilde z, which is equal to psi rs of z. Okay, now we know that the flow psi sends z to y. And actually also we know that we assume that at time s it is less than tilde y. Okay. This is tilde z. Okay, now let's see what we got. We know that psi tilde tr of y, which is equal to x, is less than z. Okay, on the other hand, psi rt of z is equal to y. It means that z is less or equal than v plus try. Okay, so we have that psi tilde try is not equal to v plus try. Next, if we look at tilde z, then psi st of tilde z is equal to y, which means that tilde z is greater or equal to v minus tsy. On the other hand, by our assumption, tilde z is less than tilde y, and tilde y is psi tilde tsy. So psi tilde tsy is not equal to v minus. This contradicts our definition of tilde psi, because we define it in the following way. We look at this point, ty. If it is left regular, we define psi tilde for all times smaller than t. We define it as v plus. And if this point is left irregular, we define psi tilde as v minus. And here we found two moments of time where psi tilde is not v plus and psi tilde is not v minus. So this is impossible. Okay, it means that we cannot assume that psi rsz is less than y tilde, hence it must be equal to y tilde. So we have proved that psi rs of z is equal to y tilde, which means that the flow sends z exactly to y tilde, and then it follows that since psi since psi rs of z is equal to tilde y, it follows that z is greater or equal to v minus sr of tilde y. Okay. Then, since z is less than tilde x, which is psi tilde of sr of tilde y, it follows that we have to define this object as v plus. And since this is v plus, the point s tilde y is left regular. Left regular means that we have some segment from y tilde to y hat that sticked to the trajectory of that starts from tilde y. Okay, it means that exists the point y hat less than tilde y with this property. Y hat is less or equal than v plus tsy, which means that psi st y hat less or equal to y. On the other hand, we choose y hat in such a way that psi st y hat is equal to psi st tilde y. Tilde y is equal to psi rs of z. So all this equal to psi rt of z, and we saw that this is greater or equal to y. It means that we have here equality, and y tilde, which is psi tilde tsy, is bigger than y hat. Y hat is sent into y, which means that y hat is greater or equal than v minus of t, than v minus ts of y. So psi tilde tsy is not equal to v minus tsy. On the other hand, psi tilde try, which is equal to x, less than z, and z less or equal than v plus try. So psi tilde try is not equal to v plus try. As we saw, this is impossible. Psi tilde must be either always equal to v plus or always equal to v minus. We get a contradiction, which means that x cannot be less than tilde x. Actually, similar considerations show that x cannot be bigger than tilde x, and finally, this proves that psi tilde is actually a flow of mappings. So the consequence of our considerations is that if we can somehow guarantee that the flow doesn't have two-sided discontinuities, then the dual for this flow exists. That's why what we do next, we will formulate some assumptions on finite point motions of the flow under which there are no two-sided discontinuities. Let's recall that finite point motions, they have the following property. The probability that trajectory that starts from x during time t deviates by epsilon is of smaller order than t at 0. In particular, for every epsilon and every delta bigger than 0, we can consider such infimum. Yeah, so this is the smallest time t, such that for some point x, this probability is greater than delta t. Here I write supremum in x, which may look restrictive, but I do this for simplification. The same works when we consider only some fixed segment on the real line and take here supremum over the segment. Okay, so we introduce the function w, which is some kind of modulus of continuity at 0 of transition functions of one-point motion. And also, let's introduce the function f. So this is actually the function ft. This is a function of epsilon. It is the probability that three trajectories of the flow didn't coalesce during time t. And starting points are x1, x2, x3 are such that distance between them is less than epsilon. If we take epsilon small, it means that we consider triples of trajectories that start very close to each other. So there is a higher chances that some of them will meet before time t. So we expect that f converges to 0 as epsilon goes to 0. It turns out that the absence of two-sided discontinuities can be controlled by the ratio of the function f and the function w. The precise result is as follows. Assume that for every time t, the limit inferior of the ratio ft over w, here the constant 8 is, I don't think that it is optimal. So epsilon and delta goes to 0, and the ratio of f8 epsilon over w is equal to 0, the limit inferior. It means that for every t, we can find epsilon n that goes to 0, and we can find delta n that goes to 0, such that this ratio also goes to 0. So under this additional assumption, we will show that the flow psi has no two-sided discontinuities, which will mean that the dual flow exists. Since we have the coalescing flow, recall that every trajectory of the flow in any after any positive time coalesces to the trajectory that started from, let's say, from the point with the rational coordinates, it means that okay. And on the other hand, we already have right continuity at all points, at all so-called fresh points. Yes. So two-sided discontinuity can appear only on the trajectory of the flow. It means that we have to check that on every trajectory of the flow, almost surely there are no points of two-sided discontinuity. Let this be S. Let this be S plus M. Yes, so we take some part of the trajectory of the flow, and we need to show that with probability 1, for all points t from S to S plus M, and for all eta bigger than 0, we can take eta rational, there are no two-sided discontinuities. So either we have such picture, so when we have a right continuity of the mapping psi t eta, or we have this picture when we have left continuity of the mapping psi t. Okay, this is not eta. This, in my notation, this is t plus eta. Okay, so let's see how our assumptions work. We can assume that for some epsilon n and delta n ratios goes to 0, take this is large number k. So this number is of order m divided by w. And let's look at partition of time from S to S plus M by points qj. So this is a uniform partition with the step size m over k. So m over k is of order w epsilon n delta n. And psi j are points on the trajectory at times qj. So this is the picture. This is the starting point sy. This is S plus M. We have a partition Q0, Q1, Q2, Q3, and so on. This point Y is Xi0, this is Xi1, this is Xi2, and so on. Okay, and let's consider two events. Event Bn means the following. So we have a trajectory that starts from Sy. We have the partition by points Qj. We have these points Xij. And together with these points, let's consider starting points at distance 2 epsilon n from Xij, plus and minus. So together with points Xij, we consider this is Xi0 plus 2 epsilon n, Xi1 plus 2 epsilon n, and so on. And also with minus. Event Bn means that during these intervals of partition, all trajectories of the flow that started from chosen points deviated from initial point by epsilon n. So in other words, all trajectories that started from marked points, they didn't deviate much from the initial point. And we can actually estimate the probability of Bn. The probability of the complement of Bn means that one of these trajectories deviated by epsilon. There are 3k trajectories, and this is the probability that each of them deviates. Yes, so we have the bound 3k by this probability. Recall that m over k of the order w epsilon delta n, actually it is smaller, which means that by the choice of w, that this probability is less than delta n. In particular, the probability of the complement of Bn goes to 0, which means that the probability of Bn goes to 1. And for large enough n, we can assume that all marked trajectories deviated from initial position by not bigger than by epsilon n. This is the first event. The second event is somewhat simpler. This is the event that trajectories that started from points qj and xij minus 4 epsilon, simply xij and xij plus 4 epsilon, didn't coalesce by time. Here is eta over 2. So in the event Cn, there are k triples. So the probability of Cn is estimated by k, our function f, which controls the probability of non-coalescing for triple of trajectories, and 8 epsilon comes from the distance between these starting points. Okay, again, recall that m over k is of order w, so we can estimate the probability as follows. Here is exactly the place where our assumption works on the ratio. In particular, probability of Cn converges to 0. It all means that for large enough n, Bn happens and Cn does not happen. Also, we can assume that m over k is small enough. Now, assume that we have a two-sided discontinuity at some point t. This point t is between qj and qj plus 1. Let's look at deviations of trajectory that started from xij minus 2 epsilon and xij plus 2 epsilon. Their deviation during the interval from qj to qj plus 1 is less than epsilon. In particular, at time qj plus 1, we have inequalities that xij minus 3 epsilon n less than this value less than xij minus epsilon n less than this is actually xij plus 1, yes, this point, which is less than xij plus epsilon, and so on. As a consequence, we see that these three values are distinct. In particular, psi qjt of xij minus 2 epsilon n is less than psi qjt at xij and less than psi qjt at xij plus 2 epsilon n. So this is psi qjt corresponding to xij minus 2 epsilon n. This is psi qjt corresponding to xij plus 2 epsilon n, and they are strictly bigger. They are strictly smaller and bigger than the corresponding point on the trajectory at which we have a two-sided discontinuity. It means that when we apply the mapping from t to t plus eta, we will also get strict inequalities. It remains to note that this lower trajectory at time qj plus 1 is bigger than xij minus xij plus 1 minus 4 epsilon n. So it's greater or equal to psi qj plus 1 t plus eta of xij plus 1 minus 4 epsilon n, and this less or equal by the same reason than psi qj plus 1 t plus eta of xij plus 4 epsilon n. And the distance from qj plus 1 to t plus eta is at least eta over 2 by this assumption. In other words, we see that we have three trajectories at distance 8 epsilon n that didn't coalesce during time eta over 2. This is impossible since event Cn doesn't happen. So these considerations show that we have some quantitative condition that under which the coalescing stochastic flow doesn't have two-sided points of discontinuity. In some cases, this condition can be verified. For example, for the Aratia flow, it can be verified. This modulus of continuity for the Aratia flow is expressed in terms of function g, and it is not hard to guess why, because we see that clear relation of function g to the distribution function of the Brownian motion. So the probability of non-coalescing triples of independent Brownian motions is estimated by some constant times epsilon cube. In particular, the condition of the theorem works if we take this exponential epsilon and delta n is 1 over n. So there is a dual flow for the Ratia flow, and we can look at its distribution. We already noted that it also must be the distribution of the Ratia flow. So if we look at the probability that the dual flow is bigger than x, it is the same as the forward flow starts from x less than y. And by some simple transformation of the integral, we see that this probability is exactly the probability of the normal distribution. And of course, I forgot t minus s here and here. So the dual to the Ratia flow is the Ratia flow. This approach can be extended, and for Ratia flows with a drift of this type, so we'll look at diffusions of such type that move independently before meeting and call meeting time. Then for such flows, dual flows also exist. And actually, the dual flow is the Ratia flow with drift minus a. Some interesting consequences of this duality. Now let's look at simply the Ratia flow. Okay, it turns out that the Ratia flow doesn't have a stationary point. Stationary point in the sense that if we act by the flow on the variable eta, we just shift this variable like along the probability space. So in the Ratia flow, there is no stationary point. On one hand, it is natural because one-point motions are just Brownian motions. On the other hand, this is a coalescing flow. Any two trajectories of the flow, they meet in some time. So they have the same limit. However, there is no stationary point. Why? Because if eta is a stationary point, if we look at dual flow that starts from the point A and B, this dual flow will coalesce at some time, and it must coalesce on the trajectory that arrives to the stationary point, and it must coincide after that with the trajectory that that arrives to the stationary point. But then, if we look at flow that is above this trajectory, then it must be above b at time 0. And if we look at the flow below trajectory, it must be below a at time 0, which means that we get a two-sided discontinuity. But we prove that we don't have two-sided discontinuities. So a Ratia flow doesn't have a stationary point. If we add the drift, and if this drift is such that the derivative of drift is strictly negative and separated from 0, then there is a stationary point. there is a unique stationary point. In fact, this point, like it attracts all the trajectories of the flow and attracts it quite rapidly. So this is the estimate probability that trajectories started from points x and y didn't meet in time t. I will not probably go into details, but this probability is obtained by a comparison of the flow with the Ornstein-Uhlenbeck process and estimating the distribution of the heating time of the Ornstein-Uhlenbeck process, heating time of 0. From estimates, one can actually show that such limits exist and are equal. And these limits are of the following type. So we look at trajectories of the flow that started from integer points at negative integer times, both positive and negative. And we show that actually we have a coalescing eta at 0 by all these points for all large enough negative n. Okay, so in some sense we get a large infinite cluster that arrives to eta at 0. And from this one can check that eta is a stationary point. Moreover, the dual theory allows to describe boundary processes. So this is the supremum of all the trajectories that arrived to eta. This is infimum of all the trajectories that arrived to eta. And if we look at these processes backwards in time, we can understand that they are related to the dual flow. In fact, if we fix the value of eta, then we can write a stochastic differential equation for these processes. It is of the form minus a dt plus dwt, like an equation for the dual flow. However, it also includes the logarithmic derivatives of the distribution of the stationary point. These terms guarantee that the upper and lower boundary processes will not meet each other after time 0. So in the end, I will discuss some questions that can be of interest for further research. Results that I presented during these lectures are about coalescing stochastic flows on a real line. So a natural next step, sorry. Okay. So the natural next step will be to extend the theory to locally one-dimensional spaces. The most natural ones are metric graphs. So these are metric spaces that segments, and branching points. So for these spaces, it is interesting to look at coalescing stochastic flows to ask whether random dynamical systems exist and to study their invariant measures. Also, it is known that stochastic flows of mappings produced by singular stochastic differential equations, they can demonstrate mixed behavior to be homeomorphic outside singular points and coalescing in the singular points or in the neighborhood of singular points. For such stochastic flows, there is no developed theory of random dynamical systems. And finally, a very interesting question that was already a little bit discussed yesterday. Up to now, it is not known whether crude cocycles of measurable mappings can always be improved to be the perfect cocycles. So up to now, there are no theorem that it is possible, and there are no known counterexamples. Okay, so that's all what I wanted to say. Thank you for the attention.
Thank you very much. Maybe someone have questions? So looks like not. So then thank you, Russell, for such a
Yeah, thank you once again.
course. And